Alright, hell yeah. Under a minute, then we'll start the video. So, angular speed is in radians per second. There's going to be 6, or like 2 pi, but it'd 6 radians in a revolution. Revolution's 24 hours, convert that to seconds. 24 times 3,600, don't know it, but that's why we're going to use our guessing skills. 2.4 times 3.6 is about 10. Cool, put that to a side. And now we're going to say 24 is 10 and 3,600 is 1,000. Watch the videos to see why, but we're going to have 10 times 1,000, that's 10,000. Sweet, plus that other 10, and that's going to be 10 to the 5. That's 100,000, that's very close to how many seconds are in one revolution. Sweet, so now we're going to take 6 divided by 100,000. We have 6 divided by 1. That's a multiplication factor of 6. Now we just have 1 divided by 10 to the 5. That's 10 to the negative 5. Times 6, and booyah, we're very close to this actual answer. Now enjoy the video. Alright, hell yeah. So we have the angular speed of the Earth, and what we're going to do is we're going to try to do this with guessing skills. Now, if you look up on Google, angular speed of the Earth is 7.27 times 10 to the negative 5 radians per second, but that's wrong because they're using a rotation speed of 24 hours. Now, if you're in the know, the Earth doesn't take 24 hours to rotate. That's going to be high noon for us, but we're also moving around a larger circle, and so we have to, 24 hours is that extra time it takes, you know what I mean, to actually get to high noon, you know what I mean, because if you know, your high noon is today, and then we rotate over here, we rotated once, but we have to rotate a little bit extra. So it's going to be 4 minutes less. So that's why the angular speed is actually 7.29. It makes our speed faster because, so anyway. But now we're just trying, I don't like this number because it's like 7 times 10 to the negative 5. A lot going on there. And then any small numbers are very difficult. Big numbers, like 10 to the 5, hell yeah, that's just 100,000. Like, we can even say that. But if you have something that's 10 to the negative 5, well, you just say 100,000, but you have to say 100 thousandths. You know, it's really complex to even say. So I think people hate small numbers, and you just don't get a very good intuitive understanding. But then this is also close to 10. This is almost 10 times 10 to the negative 5, which is 10 to the negative 4. So let's say what this is. This is 7.27 100,000ths. You know what I mean? Which is close to 10 100,000ths, which would be 1 10,000ths. You know what I mean? It's really difficult to even say these small numbers. So yeah, this is closer to 10 to the negative 4. And see how that works out? Because if I have 1 times 10 to the negative 4, but I don't have 1, I have like 0.7 times 10 to the negative 4. So 0.7 times 10 to the negative 4, that's going to be 7 times 10 to the negative 5. Alright, hell yeah. So now we're going to use our guessing skills to figure out what this is. And I guess the only other thing we need to know is that 1 revolution of a circle is 2 pi radians. Now, I did make an addendum at the end. I started this video diving into radians, but man, it gets complex, you know what I mean? Because, I don't know, radians are just a little bit tricky. Alright, so hell yeah. So this video is like, how do you do this just kind of in your head? Well, we know 24 hours, and we're going to divide. 24 hours is 1 revolution of a circle. Okay, hell yeah. So, and at the end of the day, we're trying to get radians per second. But when I do this in my head, it doesn't matter whether you get radians per second or seconds per radian. You can always, if you get this, you can always just invert the number that you get. So keep that in mind. Okay, so here we go. So we have 24 hours in a day. This is 1 revolution, you know what I mean? And so how many, and this is hours upstairs, so how many hours for, and what did we say 1 revolution was? Well, it's 2 pi radians. That's close enough to 6. So that's the other thing. I just equivocate that 1 revolution is 6 radians. Okay, so if we have 24 hours is 6 radians, well, we could do 24 divided by 6. So this is the first one we come across, and you could easily say 24 divided by 6 is 4, because that's exactly 4, but we're not going to go down that route. So we're going to go 24 divided by 6, and we're going to do this. We're going to say, hey, this is like 2 divided by 6, or it's almost 3 divided by 6. I'm just going to kind of round up to easier numbers. So I'm going to say this is kind of a multiple of 1/2. You know, it's what I'm looking at is this first digit, and I'm basically saying this is 30 divided by 6. And then I'm just looking at these first digits, and I'm saying this is 3 divided by 6, and I'm going to say that's a multiple of 1/2. And then we're going to turn this into 10 divided by 1. And we'll get to that. Actually, that might be like, why the hell did you even do that? But 10 divided by 1 is 10, and then we're going to multiply by the half, or basically half that, and we're going to get 5. So, man, that seemed like a hell of a lot of steps for something you could have probably just done. But this process will help for other numbers that are larger. Okay, so let's kind of get back to this. What's the scientific notation of this? This is 2.4 times 10 to the 1, and this is 6 times 10 to the 0. And we're going to divide these two numbers. So we can do these two steps. I always kind of like to put parentheses around these, because you can do the division in any order you want. So 10 divided by 10 to the 0, this is just going to give me 10. Okay, hell yeah. And then whatever this is a fraction that's going to be less. So right off the bat, I know it's going to be like 10, but less than 10. And this fraction, you know, it could be a third to some, it could be a half to me, and so that's kind of where I got yeah, hell yeah, let's write that in, because I just said I got kind of confused with the third, but yeah, it could be it could be between 3 and 5, you know what I mean? So that's kind of our guess. I guess 5, and it's actually 4, but we're just not too far off. And I can do this, even though that one's probably the trickier one. But okay, so let's kind of continue on. So we have this idea that 5 hours is 1 radian. That's kind of what we got. So we have 5 hours is equivalent to 1 radian. Okay, hell yeah. So now we need again, we're kind of shooting for radians per second. So we need to get into seconds. So how many seconds are in 5 hours? Well, we would need to multiply by 3,600. We're going to do that same process, but now we're going to multiply. So what's 5 times 3? Well, I don't know that, but it's 3.6 anyway, so it's almost like 5 times 4. Okay, that's going to be 20. Now, for these, I just kind of, I'm just going to write 20, or keep track of that. But now I can do that same thing. I can turn this 5, it's got 1 digit here, and I got 4 digits here. So this becomes 1 times 1,000. I can do that in my head, and that's going to be 1,000, right? That's, or for scientific notation, that's 10 to the 3. But I got 1,000 multiplied by 20, that's going to be 20,000. Okay, hell yeah. So you got 20,000. And even if you do this, you could still use scientific notation. You could say 5 times 4 is 20, but that's going to be a multiplication factor of 2, and then I just have another 10 to the 1 to keep track of. So I have 1 times 10 to the 3, and then we're going to multiply by that 10 to the 1, and then we have a multiplication factor of 2. So I have 10 to the 4, that's going to be 10,000. At the end of the day, it's 10,000, but we're going to have this 2 to carry with us, and we got 20,000. So just right there, 5 hours is 20,000 seconds. Cool. And now we have, and that's going to be the seconds in 1 radian. Okay, so we're basically there. We have 20,000 seconds, and we have that's 1 radian. But we need to flip-flop this. So we need to go 1 divided by 20,000. Alright, so let's do that same process again. 1 divided by 2, it's a factor of a half. So whatever we do, we're going to get a half, and this just becomes 1 divided by 10,000, which is 1 divided by 10 to the 4. So this just becomes 10 to the negative 4. So we have 10 to the negative 4, but we have to half this. Now, if you're good at this, then you can easily just see this is going to be 5 times 10 to the negative 5. And we're done. You know what I mean? So this is going to be the angular speed of the Earth. But I see, you know what I mean? I see how absolutely crazy guessing is. Because, I mean, like, I'm kind of used to this, but wow, it's even like teaching it. You're just going to be, I get it. You're going to be like, oh, hell no, I'm never going to do that. But it is a decent thing to do. What's the trickiest thing is to convince your brain that you're going to be okay with like 24 divided by 6, you know, is 5. Like, you know what I mean? Like, just the fact that we can say about 3 divided by 6, multiplication of half, you know, keep that in mind, but it's going to be 10 divided by 1, that's 10, that goes to 5. You know, it's just kind of interesting. So let's, yeah, let's try to do this whole thing. Alright, hell yeah. So now we're going to use the same strategy to do this with no pen, no calculator, and just try to do it in our head. So we found the angular speed of the Earth. We came up with 5 times 10 to the negative 5. You know what I mean? So not 7, but that's going to be fairly close. We're going to square that. So 5 times 10 to the negative 5. The 10 to the negative 5, that kind of... That's 10 to the negative 5 times 10 to the negative 5. So that becomes 10 to the negative 10, so keep that in your mind. The 5 squared becomes 25. So we have 10 to the negative 10, but 25, well, let's just call that 2, but we're going to have times 10 to the 1. So we have 10 to the 10, we have 10 to the negative 10, 10 to the 1. We have the radius of the Earth is... now this is where you can kind of go both ways. It's 6 times 10 to the 6. You know what I mean? So you could do that. And let's do that because we had like 2.5. We had that... well, I'll at least... No, we can keep track of that in our head. So we had that, that 2. So 2 times 6, that's about 10. You know what I mean? So we have another 10 to the 1. Cool. So we're going to have... so we're going to have now 10 to the 2, 10 to the negative 10, and this is going to be 10 to the 6. So sweet, we're going to have 10 to the 8, 10 to the negative 10, sweet. And then what's our mass? Like 70 kilograms, you know what I mean? That's going to be 100, you know what I mean? That's going to be 10 to the 2. So we have 10 to the 2, 10 to the 8, and then 10 to the negative 10. So 10 to the 2 and 10 to the negative, sorry, 10 to the 2 and 10 to the 8 become 10 to the 10, multiplied by this 10 to the negative 10, and hell yeah, those become 1. So our force for centripetal acceleration is 1 Newton. So that is kind of the guessing skills. And I'm glad I'm kind of just doing this rough. I mean, it's the first time I've made these videos or just kind of on camera, like, shared my guessing ability. But it is useful. So let's show you, so we're not just making this crap up. So what the omega is 5 times 10 to the negative 5. You know what I mean? Radians per second. I'm not going to put any labels on anything, but we're going to square that. That becomes 25 times 10 to the negative 10. Sweet. And let's not do this x anymore. So we're going to have 25, and then we're going to have 10 to the negative 10. Sweet. I think that's just a little bit easier. Radius is 6 times 10. Sorry, is 6 times 10 to the 6. You know, 6 million. This is a million. This is 6 million. Sweet. So we're going to have that. So we're going to have 6 and then 10 to the 6. Mass is going to be 70. I'm just going to call it 100. You know, plenty of people are 100 kilograms. So we're going to have 10 to the 2. Okay, hell yeah. So now we have this becomes 10 to the 8. Sweet. And then this is 10 to the negative 10. Okay, cool. We can deal with that in a second. But here, this is where I called this like 2.5 times just 10 to the 1. Cool, so let's throw our 10 to the 1 right here. And now the only things that we have to multiply are that 6 and 2.5. And that's kind of what I did in my head. I was like, hey, this is close to 10. Close enough. You know what I mean? Like I was just thinking 2 times 5. Even though it's going to be more than that, it's going to be more than 1 Newton. It's going to be less than, probably less than 2, well, it probably could be 2 Newtons. Yeah, because maybe it was too much to say this was 2 times 5. But if this was 3 times 6, that's 18, so it's not even 20. You know, it might be close to 15, sure. But I'm just showing you my guessing process, and I just called that 10. So I'm just going to say it's another 10. So booyah, this is what we had. We had that 10 to the 2, 10 to the 8. That's going to be 10 to the 10 times 10 to the negative 10. Cool, that's equal to 1. All right, booyah. So you have 1 Newton. And yeah, it was just fascinating because there's so many times that I need the angular speed of the Earth, and I just refuse. I can memorize. Nah, I refuse to memorize this number. Yeah, this 10 to the negative 5 that's difficult to memorize, and this 7.3, you know what I mean, 7.3 times 10 to the negative 5. I don't know, you know what I mean? Alright, hell yeah, we're going to end this video with this problem, kind of cool, and then we have an addendum at the very end, but it says the angular speed of the Earth around its own axis is these numbers, and we know, from our guess, it's 5 times 10 to the negative 5. This is kind of what we're shooting for. So let's use those same guessing skills. All these this pi just turns into 3. And then we have 3 divided by 4. That's about 1. So this is going to be, so I'm going to turn this into 1 divided by 10,000. And this is going to be 10 to the negative 4. Hell yeah. So this actually checks because this 5 times 10 to the negative 5 is, well, it's 7 times 10 to the negative 5 anyway, and that's closer to 10 to the negative 4. So that's kind of what we're looking for. I shouldn't have done the right answer first. Let's go to this one. This one's going to be 3, and let's just do it with no pen now. 3 divided by 3, that's going to be 1. So we're going to do 1 divided by 1,000. 1,000 is 10 to the 3 down here, so this is going to be 10 to the negative 3. We'll at least write what I think this answer is, and that's not anywhere close to 10 to the negative 4. This one is going to be 3 divided by 2. So, I don't know. I'm just going to say this is 1, but I'm just going to memorize to increase it by 50%. So, yeah, we're going to add 50%. It's not a multiple of 2. It's a multiple of 1.5. You know what I mean? So, but sometimes just adding 50%, I can do that easier. So I'm still going to say this is 1 divided by 1,000. So this is 1 divided by 10 to the 3. So we have 10 to the 3, but then we're going to multiply by 1.5. So we have 1.5 times 10 to the 3. I guess that wasn't, or negative 3. I guess that wasn't too hard. But still, nowhere close to 7 times 10 to the negative 5. All right, let's do this one. This one's going to be 3 divided by 9. I'm going to say that. I'm going to say this is a multiplication of a third. I'm going to keep that in my head. Now I'm going to say this is 1 divided by 10,000. That's 10 to the negative 4. But we have to take a third of that. All right, so this is getting a lot closer. So we have 10 to the negative 4. And we're going to take a third of that, so this becomes 3 times 10 to the negative 5. 3.3 times 10 to the negative 5. And this one might be in question, So it's in between this one and this one. Hell yeah. So, and again, this one was 3/4, so 3/4 is actually like 0.75. So this being 10 to the negative 4, it wasn't. It was 7.5 times 10 to the negative 5. And that's going to be right on the answer. So even though we used guessing skills to get 5 times 10 to the negative 5, there's no. We weren't saying that was right, but we were within a factor of 10. We didn't say this was 70 times 10 to the negative 5, and we didn't say this was 0.7 times 10 to the negative 5. Both being off. Okay, so hell yeah. So that's just using, I don't know, I'm kind of, I think I'll get better making better videos using this, or I'm just going to use this more. So again, you know what I mean, you're just saying this is 3. 3 divided by 9, we have a multiplication factor of a third. And then just say it's 1 divided by 10,000. That's going to be 10 to the negative 4, a third of that. That's the only thing with like 10 to the negative 4. And then what? Taking a third of that, it's a little bit harder. If I had 10 to the 4, and then I took a third of that, this is 10,000. I could say, okay, that's going to be just 3,000. You know, 3,300. I could do that. But with smaller numbers, it's kind of a little bit more difficult. So with scientific notation, you can do this. If I have to take a third of 10 to the 4, I can split this up into 10 to the 1 times 10 to the negative 5. Because that's exactly what you're going to be doing anyway. You know, you're going to take like 10 times 10 to the negative 5 is 10 to the negative 4. But 9 times 10 to the negative 5 is something that you would write just like this, but it's pretty much equivalent to 10 times 10 to the negative 5, which is 10 to the negative 4. That's why we're saying 7 times 10 to the negative 5 is close enough to 10 to the negative 4. So that's when we got this answer to be 10 to the negative 4. We were like, hell yeah, that's the answer. But hell yeah, so if I'm going to take a third of this, I just say what's 10 times a third? Well, it's going to be like 3.3. So that's what I'm doing in my head. You know, I should probably go over that a little bit more. But yeah, that's going to be 3.3 times 10 to the negative 5. All right, hell yeah. So I'm still satisfied with this video. Obviously we have the addendum of going over radians at the very end. So enjoy that. And thanks for joining me on this one. And that's the video. Alright, hell yeah. So I started the video, you know what I mean, with the next footage you're going to see. But I just thought we'll just use it as an addendum. Because I started explaining radians, and man, radians are kind of complex. But anyway, so that's what we have kind of at the end of this video. Thanks for joining me. Alright, hell yeah. So why would we want to find the angular speed of the Earth? Because it's useful. Because if we're at the equator, this is a top-down view, we're getting flung off. But the Earth actually spins hella slow, so we're not getting flung off very much. But that is a force that is a centrifugal force that's flinging us off. Now, how it works in physics, if we are traveling around a circle, there must be some sort of force holding us on the circle, and there's a hell of a lot of force, because we have mass, the Earth has mass, and that's kind of like a magnetic, you know, gravity is kind of... you know, it's kind of like two water droplets, you know, they kind of want to come together. I think of gravity kind of as surface tension, but that aside, we do have a force, and that centripetal force, the force that is required to hold us towards the center of the Earth, you know, F equals ma, so it's due to the centripetal acceleration. That acceleration is r omega squared. So this is going to be the radius of the Earth, and it's going to be the angular speed. And this is, angular speed is in radians per second, so we're going to get to that in a sec. Because I always just kind of joke around that no one knows what the hell a radian is, and maybe you don't, you know what I mean? But if I said, hey, let's travel like 30 degrees, or let's say 60. If I said let's travel 60 degrees in a second, you can see that we're going to swing, you know, about this. I don't know if that's about, yeah, that's about 60 degrees. That's probably a radian. That's kind of how I got this picture off the internet. But anyway, so if we do that in a second, we're going to be like 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, 6 seconds. Cool. So it looks like if I said, hey, 60 degrees in a second, well, yeah, mentally you can kind of figure out. If I said 360 degrees in a second, hell yeah, you know every second, 1 second, 2 seconds, 3 seconds, you're going to do that speed. But radians, you just need to know what a radian is, and 1 radian is about 60 seconds. So now this is kind of my little talk about radians. This is the radius. If you cut this into a string and draped it around the circle, you would get to there. So this linear or arc length, you know what I mean, of a string, if you stretched it tight, would be this radius. So there's going to be about 6 of those in a circle, and there's 6.28, you know what I mean. And that makes sense because, you know, and that's the other thing about radius or radians, because, I don't know, we use radius in a lot of our equations, but I think, from our first knowledge of circles, we use diameter. So the circumference is just pi times d, and you're just like, okay, hell yeah. But if we used radius, we would have to have 2 of those radiuses, so it'd be 2 the radiuses times pi. So hell yeah. So that would be 2 pi r. Even though that's what I don't like about equations, because it's like, hey, this 2 and this radius kind of go together. But anyway, so you have a circumference of 2 pi r. Oh yeah, hell yeah! I had to stop the video because I was just like, what the hell are we even doing? You know what I mean? Because we know that this angle is 1 radian, or that's just kind of what we're gonna call it, and we say it's taking the radius and draping around the circle. Cool. And if we do that, there is going to be 6.28. There's going to be 2 pi of those. Because that's the circumference of a circle. 2 pi times the radius. Okay, hell yeah. So that means, all right, hell yeah. This is literally the time warp, because a radian, is just the angle, but it's useful because and the fact that we deal with radians, because if you do multiply this angle in radians times the radius, you do get this arc length. Alright, hell yeah, I'm still struggling, but let's write that down. So I always do this radians. This is the symbol for angle, and we're just going to say it's radian. Radians times radius is something normal. That's arc length. Hell yeah. And then it's good to write all 3 of them, because radians per second, that's angular speed, times radius is velocity, kind of the tangential velocity. And then angular acceleration times radius is the acceleration that you would be, your tangential acceleration around the circle. Yeah, I guess this is where I just get, we just define radians as such. You know what I mean? We say that if we measure this radius and then cut a string that long and then drape it around the circle, we're going to get to there. And then we just know that there's a property of circles that this whole circumference is, 2 pi is just a number, you know what I mean? So I think it's almost better just to do this, 6.28. It's radius. And this is good. I'm glad I'm making kind of a longer video and taking a tangent, because this is a function where you have kind of, 2 different things that are totally different. Circumference is one thing, and then the radius is another. Those are 2 separate entities. They do have the same units, whether it's in meters. So we do have that. But they're related due to a proportion. So this doesn't get used enough in teaching equations, but you would have like c is equal to a constant times radius. Now this is how you make an equation and equivocate 2 different things. And these 2 different things don't even have to have the same units, because you can have this constant kind of be the go-between. And so let's do that, because the force of a spring, this is going to be in newtons, is equal to, some sort of constant times the distance, x. And that's going to be in meters. So if we have a spring at natural length, okay, right there, and then we're going to increase its natural length this much, this distance. So now it's going to be like that. Well, hell yeah, you're going to, a force was needed to pull on this to do that. And the force that you pulled on this, you know what I mean? So let's say you pulled... Alright, hell yeah, and let's do this one. Let's say this is the actual length of our spring, and we're going to pull like maybe 1 Newton. Okay, 1 Newton, just keep in mind, is about a quarter pound, and it looks like we traveled a distance of 1 centimeter. That's going to be 10 to the negative 2 meters. Okay, hell yeah. And you don't even need to do that, you just do 1 centimeter. So, cool, so you have 1 Newton over here, and then you have this spring you have some sort of number constant, and then you have a distance of 1 centimeter. Okay, so how do you equivocate these? Well, you would have to have your constant. You have to cancel out the centimeters. So you're going to have, for this constant, you're going to have a centimeters on the bottom, and then in inches on the top. No, in newtons, sorry. That just looks like 1 inch. And then the force in newtons on the top. And for this one, it's just going to be 1. But there's our units on that. And we're going to multiply it by 1 centimeter. Centimeters cancel, and you're going to get 1 newton. Alright, hell yeah. Alright, so let's stick with this. And then, yeah, because that was kind of dumb to make all these 1. So I'm going to keep this at 1 centimeter, but we're going to say that this was a force of 4 newtons. So, hell yes, we get 4 over here. So we have 4 newtons is equal to the spring constant times, we pulled at a distance of 1 centimeter. So to get 4 over here, the spring constant has to be 4 newtons per centimeter. And then if we multiply that by 1 centimeter, centimeters cancel, we get 4 newtons. So hell yeah. So in that case, our spring constant is 4 newtons per centimeter. And now we're kind of representative because hell yeah, because and now we can go back to this. So the circumference is always going to be bigger than the radius. So we have a proportion that's going to be bigger than 1, and it's going to be 6.28 times the radius. You know what I mean? And I think that's worthwhile to go over because I don't know, pi just because it's a Greek symbol. I think people lose touch that it's actually a number, and it's pretty close to 3. And people even kind of joke, like there's the biblical joke that, you know, they were saying the circumference of a circle is 3, and I kind of follow that kind of stuff, and then people were all complaining about that because it's not right, but hell no, it's 3 checks on that. You should always think pi is basically 3. 3.14 is super close to 3 than it is to anything else. Alright, so hell yeah. Okay, so that was definitely not where I wanted to take this video right off the bat, so I might actually put this bonus content at the end. But let's see where we were going with this. We have this equation for force, centripetal force, and mass and acceleration. Acceleration is radius, and then we need our angular speed in radians per second. And you know, for this equation, we need angular speed, and we need to square it, and then we need to multiply it by the radius of the Earth. This video is not going to go over that, but it's a precursor to that, because to prove this, you know what I mean? There's you know, you at least need to know this angular speed of the Earth term. And so this video, I was just like, well, let's try to figure out the angular speed as quickly as possible. Like, how do we do that? Alright, hell yeah. So, anyway, this has been an addendum, but I definitely wanted to cover what a radian is. And because I need to do that every time, you know what I mean? Just because it's such a bizarre concept that you're defining a radian as such. You're taking the radius, draping it around a circle, and that arc length you're calling, hey, the angle that makes that arc length, that's 1 radian. And I don't know. You know, this whole thing is just to get to the fact that, hey, the full circle, like 1 revolution is equal to 2 pi radians. You know what I mean? So that's kind of your, and then let's write this. I like to stack them. 1 revolution is 2 pi radians. So now you can write it that way, and then I would flip it over. 2 pi radians is equal to 1 revolution. Alright, hell yeah. And I would write it another way. I would say 2 pi radians, because what's 1 revolution? That's 360. And then I would write this out, DEG. Anytime that you use in degrees, it's just going to be way better for you to write DEG instead of doing like a little circle, superscript. Alright, so then we're going to write the other one. We're going to do 360 degrees divided by 2 pi radians. I'm just doing this because these are your useful tools when you're using the factor label method to switch units up. Okay, hell yeah. So this will be kind of at the end of the video, but now, I mean, what we're going to do is we're going to try to get the angular speed of the Earth, you know, in kind of a timely manner. Let's see if I can even do that.